All right, let's talk about a huge concept in artificial intelligence, the intelligent agent. You probably hear this term thrown around all the time, right? Well, by the end of this, you're going to know exactly what it means and why it's the fundamental building block for pretty much everything, from your smart home device to a self-driving car. So let me ask you a question. What could you, a robotic vacuum, and a self-driving car possibly have in common? I know, it sounds like the setup for a really weird joke, but the answer gets right to the heart of AI. The thing is, all three of you perfectly fit the definition of an agent. And this right here, this is the core idea in a nutshell. An agent is just something that exists in some kind of environment. It uses sensors to figure out what's going on, and then it uses actuators to, well, to do something about it. This super simple loop, perceive, think, act, is the foundation for absolutely everything we're about to get into. Okay, so with that simple loop in mind, let's get a little more formal. We're going to break down the essential components, the building blocks that officially make something an AI agent. Here it is, the textbook definition. An agent perceives its environment using sensors and acts on it using actuators. The easiest way to think about it is that sensors are for taking information in, and actuators are for getting things done in the real world. And this is where it really clicks for most people. Think about yourself. As a human agent, your sensors are your eyes, your ears, your sense of touch. And your actuators? Those are your hands, your legs, your voice. For a robot, it's the same idea, just different gear. Its sensors are things like cameras and GPS, and its actuators are motors and wheels. See? Same concept. All right, theory is great, but let's see this in action with a classic example. We're going to look at one of the simplest agents you can possibly imagine, a little vacuum cleaner bot. So let's imagine a super simple world for our little bot. I mean, ridiculously simple. It's just two squares, A and B, and each square can either be clean or dirty. That's it. The agent's sensors can tell it two things. Which square am I in, and is it dirty? And it can only do three things. Move left, move right, or suck up the dirt. Now, this table is basically the agent's entire brain. Seriously, it's just a list of simple if-then rules. If its sensors say, hey, we're in location A and it's dirty, its programming says, okay, action is suck. If it perceives location A and it's clean, the action is move right. It's just a direct, simple map from what it sees to what it does. But here's the thing, just acting isn't good enough. We want our agents to act well. And this brings us to a really critical idea in AI, rationality. How do we measure if an agent is actually doing the right thing? So what makes an agent rational? Well, it's an agent that always chooses an action that it expects will maximize its performance measure. That's a fancy way of saying it always tries to get the best possible score. For our vacuum bot, the best score might mean cleaning up the most dirt in the shortest amount of time. It's all about aiming for the best outcome. And this is a super important distinction to make. Being rational is not the same as being omniscient or all-knowing. An omniscient agent would know the future, right? It would know exactly what's going to happen. But that's impossible. A rational agent is just making the smartest play with the cards it's been dealt. It does the right thing based on the information it has right now. Okay, so if we want to build one of these rational agents, how do we even start? Well, AI engineers have this fantastic framework they use called PEAS. You can think of it as the universal blueprint for mapping out any agent you want to design. PS stands for Performance, Environment, Actuators, and Sensors. And to design an agent, you really just have to answer 4 questions. For performance, you ask, how do we measure success? What does a good job look like? For environment, where is this thing going to operate? And we already know actuators and sensors. What can it physically do and what can it perceive? So let's take this framework and apply it to something way more complex in our little vacuum bot. Let's talk about an automated taxi. Now we're dealing with a powerful, real-world agent that has to survive in a messy, chaotic, and totally unpredictable environment. And here's what that PEAS breakdown looks like. The performance measure isn't simple anymore. It's a combination of safety, speed, staying legal, and even making sure the ride is comfortable for the passenger. The environment? Oh, it's roads, traffic, pedestrians, weather, crazy complex. The actuators are the steering, the accelerator, the brakes. And the sensors are a whole suite of things. Cameras, GPS, sonar, you name it. Nailing this down is always step 1. So now that we know how to define agents and how to start designing them, let's look at the different kinds. There are 4 basic types. And you can really think of them as an evolutionary path, or like levels in a video game. Each one is more complex and more capable than the last. First up, we have the simple reflex agent. This is level 1, it's the most basic type there is. You can see from the diagram, it's a straight line. Information comes in from the sensors, it triggers a simple rule, and an action immediately goes out. Bam! Done. The most important thing to know about this agent is that it has no memory. Zero. It only acts on what it sees in the present moment. Think of a simple thermostat. If it senses the room is cold right now, it turns on the heat. It has no idea it was warm 5 minutes ago. Our little vacuum bot from earlier? A perfect example of a simple reflex agent. Okay, let's move to level 2, the model-based reflex agent. Now look closely at the diagram. You see that new box in there labeled state? That changes everything. This agent has a memory. What this agent does is maintain an internal model of how the world works. It uses its memory of what it's seen in the past to help it understand things it can't see right now. A self-driving car absolutely needs this. It has to know that a car that just drove behind a big building is still there, even though its cameras can't see it for a second. That's its internal model at work. Now for level 3, the goal-based agent. We've added another new concept here, goals. This is a huge leap because it allows the agent to not just react to how the world is, but to think about how it wants the world to be. It has an ambition. By having a clear goal, the agent can make much more intelligent decisions. It might choose an action that seems weird or even counterintuitive in the short term because it knows it's a step toward achieving a long-term goal. For that self-driving taxi, the goal might be get the passenger to their destination, and that goal informs every single turn and lane change it makes. And finally, we arrive at the most sophisticated type, the utility-based agent. See, sometimes just reaching a goal isn't enough. There might be lots of ways to get there. Some are faster, some are safer, some are cheaper. This agent has what's called a utility function, which is basically a way of scoring how good or happy a particular outcome is to help it choose the best path. That utility function lets it weigh all the trade-offs and choose the option that maximizes its overall happiness, so to speak. And that brings us to a really fascinating final question. We are the ones building these agents. We're giving them goals and defining their sense of utility. But as these systems get more and more powerful and autonomous, who gets to define what a good outcome really is? That's a question that everyone, not just AI researchers, is going to be thinking about for a long, long time.